Okay, so we're starting a motion problem. We know that because we're told information at the start of the question which says that a particle is moving. So that's going to tell us that we're going to be using our Suvat equations. Okay, so reading through, we've got a particle moving in a straight line from A to B with constant acceleration 3 meters per second squared. As soon as we're told that there's constant acceleration, that means that we can use our Suvat equations. They will hold. We're also told that its speed at A, where it's starting from, is 2 meters per second, so that tells us it's going to be an initial velocity, and we're also told that it takes 8 seconds to do that motion from A to B. Okay, so we're going to start with our sketch to get all of our information on a diagram, and then we can start looking at the data. Okay, so we've got our straight line from A to B. And reading back through, we know that we've got constant acceleration, 3 meters per second squared. So we're going to represent our acceleration with a double arrow. We're told the speed at A is 2 meters per second, so we'll mark that on at A. And we show that with a single arrow. Okay, and finally we've got that T is 8 seconds, so we can just put that time in our data table. Okay, because in kinematics and motion we're dealing with vectors, the first thing we need to do before finding our data is to define a positive direction. So I'm going to choose my positive direction to be going from left to right, as that's the same direction as the particle is travelling in, but you could choose the other way if you wish. Now that I've defined my positive direction, I can start thinking about whether each of my Suvats are positive or negative. So, I don't know the distance, I haven't been told anything about that. I do know the initial velocity, I'm told that it's 2, and as it's going in the same direction as my positive arrow, then it's going to be positive 2 meters per second. My final velocity by the time I get to B, I'm not aware of yet, but I do know the acceleration, and again that's going in my positive direction, so that's going to be positive 3 meters per second. Right, so now we're ready to start doing our calculations. So in part A, we're asked to find the speed of the particle at B. So that's going to be us looking for the final velocity. Now so far, we know U, A and T. So we have to have an equation that has U, A and T, and as we're asked to find the speed, we're also going to have V in it. So looking at the formula on the right hand side, I'm going to select V equals U plus AT. Substituting in my values then, I don't know what V is, so I'll keep that as V equals 2 plus 3 times 8. So the velocity equals 26 meters per second. Part B. I'm going to try not to have to use the data that I calculated in part A, just in case I made a mistake. That way I'm only going to make a mistake in one part. So I'm going to only deal with U, A and T, which I know, and I'm asked to find the distance, so that's going to be the displacement S in this case. So I'm looking for a formula involving S, U, A and T. Again, looking at the formulae box, we're going to have S equals UT plus a half AT squared. I'm going to substitute in the values, 2 times 8 plus a half times 3 times 8 squared. So the displacement is going to be equal to 16 plus 32 lots of 64, which are 96. So I'm going to have my displacement equal to 112 meters. Okay, so that's our full workings through. In this particular question, all the units that I were given were consistent. So my velocity was given in meters per second, so I would expect my acceleration to be in meters per second squared, and as we're dealing with seconds, so is the time. However, if any of those units didn't agree with each other, before we started using the data, we would need to convert them all to the same units. So here we are again with another motion problem. We've got another particle moving in a straight line from point A to point B. So I'm going to start off in the same way by drawing my nice straight line and then marking on the points A and B. This time in the question I'm told that there is constant deceleration, so I'm going to draw my arrow backwards. and label that with 1.2 meters per second squared. Again, remembering my double arrow represents acceleration. I'm told about the time, that it takes 6 seconds to move from A to B, so we're just going to mark that on our diagram, t equals 6 seconds. Speed of the particle at B is 2 meters per second, and it also tells us that the direction hasn't changed. So that means that as it was going from A to B, then its velocity is still going to be going in the same direction of 2 meters per second. And we're asked to find the speed of the particle at A and the distance from A to B. Final thing before starting to get our data, we just need to mark on our positive direction. As it's going from A to B, I'm going to choose my positive direction to be left to right. Okay, so displacement, we've got no idea about that yet. Initial velocity at A, we're not told anything about that. Final velocity at B, we are told something about that. That is 2 meters per second, and it's going in my positive direction, so 2 meters per second. And the acceleration is going against our direction of travel, so it's going to be minus 1.2 meters per second squared. Our time of 6 seconds can also go into our data table. So any equations that we're using are going to have to involve v, a and t, because we've only got those 3 bits of information. So for part A, we're asked to find the speed of the particle at A, so we're going to be looking for u. So I need an equation involving u, v, a and t, and therefore I'm going to select this one just here, v equals u plus at. Okay, so I'm going to have to do a bit of rearranging in my formula, and I'm going to choose to do that after I've substituted in the values. So I've got 2 equals u plus minus 1.2 times 6. Before I move anything else around, I'm going to try and simplify it. So I've got 2 equals u minus 7.2. And then in order to rearrange, I can add the 7.2 to both sides. So I'm going to get u equals 9.2 meters per second. Nice clear answer. Okay, for part B, we are looking at the distance from A to B. So that's going to be looking for our S. So now I'm looking for an equation involving S, V, A and T. And that's going to be the third one in my list. So S equals Vt minus a half At squared. Not much rearranging to do here, as it's got S as the subject already. So we've got S equals 2 times 6 minus a half minus 1.2 times 6 squared. So my final answer is coming in at 33.6 meters. Okay, so we've got a CVAT equation again. We've got a particle, so we know that we can ignore air resistance and we can ignore any rotational motion. We've got constant deceleration of 2.5 meters per second squared, and we know that there's movement in the positive direction of x, and we've got a speed of 15 meters per second once it's past that origin O. So starting off with our diagram, we know that we've got movement in the positive x direction. I know my deceleration is going to be acting opposite to that, so that's 2.5 meters per second squared. The 15 meters per second, if we read back before that, that's when it passes the origin O. So I'm going to mark on the origin O, and then I can draw my arrow saying it's moving this direction with a velocity of 15 ms to the minus 1. Okay, now thinking about this, it's starting off moving in the positive x direction, so my particle is going to start going this way, but as it's decelerating, eventually that's going to decelerate down to 0, so it's going to instantaneously stop, and then it's going to take a path back in the opposite direction. So that dotted line there is just going to show the expected path of my particle. Obviously not with the big curve, but that's just to represent where it's going forwards and backwards. Right, marking on positive direction makes sense to put it in the same direction as the positive x-axis. Looking at the data, we know nothing about the displacement or any distances. We do know that the initial velocity is 15 meters per second. We don't know anything about the final velocity at any particular point, apart from we do know that at the instant when it changes direction, that's going to be a speed of 0 meters per second. So that might be something we're going to use later. The acceleration is going opposite to my positive, so we've got 2 minus 2.5 meters per second squared. And time is not something that we're given either. So at the moment we've only got 2 pieces of data. So it looks as if we are going to have to use that specific point where v is equal to 0. First of all, we're asked to find the time between the instant when P first passes through O and the instant when it returns to O. So in this case, we're not thinking about distance with Suvat, we're thinking about displacement. So by the time it's returned back to the origin, it hasn't actually changed position, therefore its displacement is 0. So for this part of the question, we can treat S as being equal to 0. So now we've got S, U and A. We're selecting our formula, and we're trying to find T. So we're looking for one with S, U, A and T, which is going to be S equals UT plus a half AT squared. Right, so we know that our displacement is 0. We've got 15T plus a half times minus 2.5 T squared. Now looking at this, I've got one variable. However, I have got a variable in t squared, so I'm expecting to be solving a quadratic here. So I'm going to do a bit of rearranging, and I'm going to bring my t squared to be positive. So I'm going to have 1.25 t squared, and I'm going to bring the 15t across as well, and that's still going to be equal to 0. Now, if it wasn't equal to 0 on that side, and we did have a coefficient of units, then we would think about using the quadratic formula, whereas in this case we can simplify matters by factorising with t. So we've got 1.25t minus 15 being equal to 0. And there's 2 possible solutions here. Either that this original t, which it might help you to consider is inside its own bracket, could be equal to 0, or our alternative solution here, t could be equal to 15 over 1.25, and using our calculator, which we're able to do, we can say that that is equal to 12 seconds. So it does ask us for the time between the instant when it first passes through T and the instant when it returns to O. So therefore we've got to think about the difference in time between those two, so we're going to do 12 subtract 0. So my final written answer for part A is going to be the total time is 12 seconds. Right, on to part B. We're now looking at the total distance travelled by P in this time. Now, we're given the time now, so that's now an extra piece of information which we could use if we wanted to. However, because the displacement there is 0, we're going to have to be a little bit more savvy about this because it wants the total distance, so it's looking for our journey out and back. So what we might want to consider is breaking it into 2 parts, going from O to its maximum point, which we could give a letter here of M, and then from M to O, which we know is going to be the same distance. So we might want to reconsider Suvat here. So this time, S is what we're trying to find out. We still know that the initial velocity is going to be 15, but this time we can say that v is equal to 0 for the halfway point. Okay, so v is equal to 0 at M. So now we've got 3 bits of data. We've got U, V and A, and we're going to find the displacement from O to M. So that's going to be S. So we're going to use v squared equals u squared plus 2as. Subbing in our values, so v at that point M is 0 equals 15 squared plus 2 times minus 2.5 times our displacement S. Okay, so we're going to use our calculator. We're going to do a bit of rearranging. So we've got 5S equals 225, and therefore S has got to be equal to 45 meters. So that's our displacement from O to M. So therefore my total distance is going to be twice that. So my total distance is going to be equal to 90 meters, going from O to M and then back from M to O. Okay. Okay, so we're starting to get used to these SUVAC problems now. So this one you're going to read through by yourself first, and then see if you can go ahead of the explanation, and then just double check when you've finished. Right, so in this question I'm told that I've got a ball and it's projected vertically upwards. Now as soon as I know it's projected vertically upwards, I'm immediately going to start thinking that gravity is involved. So on my diagram I'm going to draw gravity acting down, g equals 9.8 meters per second squared. That's definitely going to be involved here. Okay, now it's projected from a point X, which is 7 meters above the ground. So we ought to draw on our ground level and then our 7 meter level as well. So marking that dimension on as 7 meters. Right, I'm going to change colour for the motion of my particle then. So I'm going upwards with an initial velocity of 21 meters per second. So my particle is going to go up until it decelerates sufficiently due to gravity that it's going to fall back down to the ground again. So that black dotted line there is going to be the motion of the particle. Right, we're asked to find the greatest height above the ground and the time of flight of the ball. Before I can do that data, my one final thing to add on is my positive direction, and I'm going to choose that to be upwards. So, filling in the data table, as of yet I know nothing about the displacement. I know that my initial velocity is going to be 21 meters per second. I know that my final velocity at the top is going to be 0 meters per second, and I'm also very aware that it's not going to be 0 meters per second at the bottom, because we're thinking about the speed at which it hits the bottom, not what it slows down to once it's hit the bottom. I know that my acceleration is 9.8, and it's going opposite to my positive, so it's going to be minus 9.8 meters per second squared. Okay, and I know nothing about my time. Back on part A then, we're looking for the greatest height reached above the ground, and as we're looking for that greatest height, that's going to be where our final velocity is 0 meters per second. Anytime where it asks for your greatest height, that's going to be where the velocity is 0. So I know V, and I've got U and A, and I'm looking for S, so I'm going to be using V squared equals U squared plus 2AS. So 0 squared equals 21 squared plus 2 lots of minus 9.8 times the height which we are trying to calculate. So rearranging that, we are going to end up with 21 squared divided by 2 lots of 9.8, which is going to give us 22.5 meters. And I'm underlining my answer. On to part B. We're now looking for the time of flight of the ball, and what we want to consider here is the total displacement that the particle has gone under from its starting point to when it hits the ground. So although it started at this point just here, it finished there. So when we're looking at the displacement, not the distance, we want to be thinking what's the movement from where it started to where it finished, and that displacement is down, so therefore my displacement is going to be minus 7 meters. So I know S this time, I know U and I know A, and I'm asked to find T. So we're going to be using S equals UT plus a half AT squared. So minus 7 equals 21T plus a half lots of minus 9.8 times T squared. Again, I'm looking for that T squared term. That's going to tell me I've got to solve a quadratic equation. So the first thing I'm going to do is rearrange getting all my terms onto one side and setting them equal to 0. And from there I can either choose to factorise or to use the quadratic formula. So that's going to give me 4.9 T squared minus 21T minus 7, and that's equal to 0. Probably our easiest option here is to use the quadratic formula. So we've got our A value of 4.9, b minus 21 and c minus 7. So subbing that into the quadratic formula, which is t equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Now at A level you will be expected to remember that formula by heart, so let's start learning it now if you haven't already. Subbing in the values then, we will then be able to calculate the value of t. So our positive value, our positive root comes out to be 4.60 seconds. And if we're careful with how we use our calculator, we can then quickly change from the positive to the negative, and that's going to give us a time of minus 0.311 seconds. Looking at that, we know that we can immediately discount anything which is a negative time, but thinking about it, that time has come from assuming that the particle was released from the ground level rather than where it was at point x. So we know we can definitely ignore that one, so we can put a nice line through it, but it's good to show that you have considered that route, and therefore our total time, the time of flight of the ball, is 4.60 seconds. So this next problem is quite a common style of exam questions, as no longer is the ball being projected from ground level, but instead it's being projected from a point above the ground. So we could start off our diagram by having the ground level, and then the point at which it's projected from, and making that really clear that is 7 metres above the ground. So then from this point, it's being projected upwards with a speed of 21. It's going to go up to its point at which the velocity is going to be 0, and then it will come back down to the ground level again. It's vertical motion, so acceleration is acting downwards with 9.8 meters per second, and I'm going to mark on my positive direction as upwards this time. So we'll start getting our data for part A. We are looking for the greatest height reached above the ground, so that's going to be at the point at which the velocity is instantaneously 0, so we'll fill that in straight away. Displacement is what we're trying to find. U we know to be 21, and acceleration is due to gravity, so it's minus 9.8. With these variables, S, U, V and A, we are going to use V squared equals U squared plus 2AS. Subbing in, 0 squared equals 21 squared plus 2 lots of minus 9.8 times by S. And if we rearrange, we're going to get 19.6s is equal to 21 squared. And that's going to give us a displacement of 22.5 meters displacement. Okay, now thinking about that, that's from the point at which it was released. And as the question asks for the greatest height above the ground reached by the ball, we're going to need to do 22.5 plus the 7, which it initially started from, to give us our final answer of 29.5 meters. In part B, because we're changing what we're considering, it's useful to do another data table. So part B, we will again do our SUVAT values. So this time we're looking for the time of flight of the ball. Now the time of flight is the time taken from the point at which it's released, which was the original point x, to when it's going to hit the ground. So in that time, if I'm still taking it up to be positive, the displacement is going to be down 7 meters, so that's going to be equal to negative 7. My initial velocity is still 21. The final velocity is not important for this question. The acceleration is still 9.8 acting downwards, so it's negative, and time is what we are trying to find. So we've got S, U, A and T. We are using S equals UT plus a half AT squared. So negative 7 equals 21t plus a half lots of minus 9.8 times by t squared. We've got terms in t and t squared, so it's a quadratic. We're going to rearrange that and set it equal to 0. 4.9 t squared minus 21t minus 7 is equal to 0. So t is equal to 21 plus or minus the square root of 21 squared minus 4 lots of 4.9 times negative 7. And that is all over 2 lots of 4.9. That's going to give us two solutions. So t is either for our positive answer, is going to be 4.60, or if we change the sign and look for our negative answer, our other one is going to be negative 0.311. Now we know that a negative time isn't applicable to this question, so we can ignore that, but it's good to have written it down to show that we've considered it, and we can say that the time is equal to 4.60 seconds. So once again here we're looking at vertical motion. We're going to start off with our sketch. As we know that it's thrown vertically upwards from the point O, so point O normally refers to the origin, so that's going to be our starting point here with a velocity of 30 meters per second. We know it's thrown vertically upwards, so we also know that gravity is going to be important, so acting downwards with an acceleration of 9.8 meters per second squared. And we're asked to find the total time for which the ball is 20 meters above its point of projection. So we can draw a nice dotted line there and represent that relative to the base with a distance of 20 meters. So that's the distance we're going to be looking for in our CVAT equations. I'm going to pick my positive direction to be upwards, and I'm just going to mark on the path that I'm expecting the ball to take as it comes back down to the ground level after decelerating due to gravity. So, filling in our data table, we're asked to find the total time for which it is 20 meters above its point of projection. So, looking at the diagram, we can see that the ball is going to be exactly 20 meters above its projection points at 2 points, here and here. So if we can calculate the two possible times where it's there, we can therefore look for the total time in between those two where it is following this path here. So we're looking for a displacement of 20 meters, and it's 20 meters up from the original point, so positive 20 meters. Initial velocity 30 meters per second. Final velocity at the point at which it's at 20 meters, we have no idea. We're not sure what speed it's going at that stage. Acceleration is due to gravity, minus 9.8 meters per second squared. And the time is what we are looking to calculate. So SU and A is our data, T is what we're trying to find, so we're going to be using S equals UT plus a half AT squared. Subbing in, 20 equals 30t plus a half minus 9.8 t squared. Okay, again I can spot that t squared term. I'm looking at a quadratic, so I'm going to rearrange and make it equal to 0. So 4.9 t squared minus 30t plus 20 equals 0. And I'm expecting to use my quadratic formula. Hopefully you are starting to remember this formula now. Okay, so we're going to sub in our values. T equals 30 plus or minus the square root of 30 squared minus 4 times 4.9 times 20. And all of that is going to be divided by 9.8. So one of our solutions is going to be 5.36 seconds, and our alternative solution is 0.76 seconds. We're asked to find the total time for which it's above 20 meters, so the total time is going to be equal to the difference between these two, 5.36 minus 0.76, which is equal to 4.60 seconds. And there we are.